And the points that stick out the furthest that way are the current records. The broken records don't compete, right? So it's pretty clear, and I think that I'll consider that proof by intimidation of this lemma, right? There's a proof written here, but that's pretty easy to see. And so what distribution does Fn plus have for fixed n, or more generally, what distribution does the stochastic process F plus have? Well, we're just taking, remember that each x plus super k has a gamma distribution with parameters d and 1, right? So we're just taking a partial maximum process, and that has been studied dating back to work of Jack Kiefer in 1972, okay? I didn't include references, the details of the references in the slides, but they're in the papers that I mentioned, okay? And what did Kiefer do? Well, it's rather sophisticated use of the Borel-Cantor lemma. When I say sophisticated, it means things like you have to use some monotonicity of the process, monotonicity of boundaries, and then you have to look not along every time, but along a certain very carefully chosen sequence of times and so on. So it's elementary but sophisticated use of the both Borel-Cantor lemmas. Okay, and anyway, here's how it turns out. It's kind of interesting. The answer is interesting too, right? Typically, Fn plus differs from log n by exactly of order log n, at least when d is greater than or equal to 2, which is the only interesting case. And in fact, typically Fn plus is like log n plus d minus 1 times log n. But occasionally, Fn plus gets somewhat bigger than that. Occasionally, Fn plus gets about as big as log n plus d times log n, rather than d minus 1 times log n. And in fact, using techniques very much like exercise 1B in the current homework for 553.721 about the run length process, you can show that not only is almost surely the lim sup d and the lim inf d minus 1, but the set of limit points of the sequence is all the points in between d minus 1 and d. That's pretty easy because to prove once you know this, because what happens is Fn plus stays constant for a while log n behaves smoothly, so you sort of drop down smoothly from the big values to the small values. Then you jump up when Fn plus becomes unusually large, okay? What about Fn minus? Well, the B implies A, right? At least when D is greater than or equal to 2. That is, as I said, Fn minus differs from log n by something that's almost surely of smaller order of magnitude than log n, okay? If there's time, I'll come back to the proof of that. And Svante Jansson has some conjectures in my talk because I gave a talk, a shortened version of this talk at Analysis of Algorithms meeting in June in France. Svante was in attendance, and as Svante always does, he figures everything out in real time and gives you notes afterwards saying, oh, figured it out. So I'm saying conjecture, but that's just because I haven't worked through the details of Svante's notes yet, right? And he only did it when d equals 2, but he's probably right in general. That is, he thinks that in fact, Fn minus is like log n minus log n, and in fact, probably even up to a constant term like that, okay? But for the purposes of getting the width to lead order, we didn't need to know that, right? So putting together what we do know about Fn plus and Fn minus, you get that the typical behavior of the width is that divided by log n, it converges in probability to d minus 1, and the almost sure behavior is like it was for Fn plus, right? Because Fn minus is negligible, and in particular, the width is exactly of order log n, almost surely. Well, that's, we had to be careful writing this. That's true if d is greater than or equal to 2. This remark down here says, well, when d equals 1, there is only one current record at any particular time. So Fn plus is Fn minus, so Wn is 0. And this still holds true when d equals 1. But when d equals 1, this doesn't hold, right? So, okay. And the result about all the limit points can be carried over from Fn plus, carry over immediately from Fn plus to Wn. Okay, so now the question is, how do we learn? So Fn plus was just applying the results of Kiefer about extreme value theory. Fn minus was more challenging, right? And so I'll maybe have time for at least some of this. Let me try to explain a little bit about what's going on. So in looking at Fn plus, we were interested in the largest value among the sum of coordinates for any of the observations up through time n. For Fn minus, we're going to make use of what I'll call B sub m comma n, the mth largest value among them. Okay? And then the claim is in this lemma that over the event that there are at least m remaining records at time n, the Fn minus is less than or equal to Bmn, which is obvious, right? Because Fn minus is the smallest sum of coordinates. So if there are m current records and you take the mth largest one of those, that's certainly an upper bound on Fn minus. Okay, and for technical reasons, it's useful to observe that the processes F super minus and this process Bm dot, that they have non-decreasing sample paths. That's also pretty good to prove. Okay, this next lemma says there are pretty many remaining records at time n relative to n, at least about log n over d times log n. We can beef that up a little bit too, but I won't go through the details of that. And putting those two together, you get that Fn minus doesn't get much bigger than log n. It gets bigger on the scale of log n by a negligible amount. So the upper bound on Fn minus is easy. This is an upper bound. I mean, the probability of it being large is infinitely often is 0. But for the lower bound, how do we argue? Dan discussed this in the seminar last year, so this is sort of a rehash, but it's a terrific geometric lemma that Dan presented, and I want to present it again here. So, okay, so we're going to use the definitions of the frontier and the closed record-setting region, and we're going to argue as follows. So I want an upper bound on this probability to get a lower bound, a lower stochastic bound on Fn minus, okay? So clearly this event is the same as this one, and is the same as that one, right? So what does it mean for x to be in the record-setting region? It means that it's not dominated by any of the observations up through time n, right? That's just the same thing as saying that the number, I explained the notation up here, the number of observations in the orthant with vertex x, the positive orthant with vertex x, is 0 for some x in the range with x plus less than or equal to b, okay? For some x greater than or equal to 0 here, okay? And you can check easily enough that the condition x plus less than or equal to b can be changed to the condition x plus equal b. So we're asking for an upper bound on the probability of a union, but students even at the beginning of 553.720 know it's okay to be dealing with the upper bounding the probability of a finite union by finite subadditivity or a countable union by countable subadditivity, but this is an uncountable union. And the question is, how can we upper bound this probability? And the answer is this beautiful geometric lemma of Dan's, which says that, so again, we want an upper bound on this probability. Think of the value b in this last expression as being the corresponding to the sum of coordinates along this blue line. Take a black line a little further away from the origin, and what this geometric lemma says is that every point along this blue line has one of these regularly spaced black points in its orthant. And therefore, if there are no points in any of these blue orthants, one for each, Dan used to, I should have used your slides. You had a nice set of slides where like you slid this along here, right? I simplified it down to one picture. Slide this along here, you'll always have a black point on this line in the orthant, right? And therefore, if there are no points in any of the blue orthants, no points in any of the blue orthants, then there must be no points in any of the black orthants. But that now is a finite union whose probability we can upper bound, and I'm running short on time, so I'll skip the rest of the details. But that works together with a somewhat sophisticated first Borel-Cantelli argument to get the result that we need on the stochastic lower bound on F minus. Okay, so for further details, read the Frontiers paper. All right, the final segment of this talk is about record breaking. I like to refer to the paper I wrote about this as my record breaking paper. It's rather nice. Okay, so Dan also presented this set of data in last year's talk and pleaded with us to figure out why this is true, and I was able to do that.
I think I did it several years before that.
Okay,
Right,
so
it only took him an hour once he got within an hour.
you or some predecessor of yours. Okay, so Dan had generated 100,000 bivariate records, and each time that a record was generated, he saw how many records were broken. And out of the 100,000, 50,334 times no records were broken, and 24,667 times one record was broken, and so on. And you got to admit, this looks pretty geometric, right? It pretty much looks like half the time no records are broken, a quarter of the time one record is broken, an eighth of the time two records are broken, and so on, right? And so I was able to prove something like that. Not quite the same, because I'm going to look not in records time, but in observations time. And so sometimes there won't even be a record set, let alone breaking any record. So I have to condition on the observation setting a record. And I'm not counting up through a particular time. I'm just going to take one late time. So there's some differences, but here's the result. So consider our null bivariate model for observations. Let's code the number of records killed or broken at time n by -1 if the observation isn't even a record. Okay? But if it is, then let's let Kn denote the number of records killed by the nth observation. Right? Then the claim is that Kn, conditionally given that Kn is greater than or equal to 0, conditionally given that the nth observation is a record, converges in distribution to this shifted geometric, right? Geometric with values 0, 1, 2, and so on, where the success probability for the geometric is 1/2. Yes?
So if I ratcheted it up to more than bivariate dimensions, where's the d equal to 2 showing up here?
Okay, well, next slide is about dimension higher than 2. This is the paper I wrote about dimension 2. And when I wrote the paper, I had absolutely no idea how to extend beyond dimension 2, because the techniques used are really highly restricted to that. Okay? And then I gave a talk about it with Svante Janssen. And he has, I think in this case, even he isn't sure what the answer is, but he has a conjecture as to what it is. You'll see what it is on the next slide, which is my last slide, the next one. Okay? So in this paper, I spell out what would have to be done in order to soup this up, and I'm still talking about d equals 2, soup that up to saying that the fraction of times up through, in records time, up through capital M, that you've broken K records converges to the geometric probability, and uniformly in K. It all comes down to certain variance calculations, as I show in the paper, but the variance calculations are elementary, but seem to break down into a bazillion cases. So that's something that maybe a student will
So
look
Dan's
into.
question, the direct one, it remains a little bit tricky, and you get.
Yeah, that's right. This I considered in the direction of explaining. I mean, at least that shows, in some sense, how geometric 1/2 pops up. By the way, the proof is rather computational, and I still don't even, I can't say after writing the paper that I really understand why it's geometric 1/2. You know, I mean, there's nothing where I could say, oh, the hidden geometric 1/2 random variable is just this thing, right? No, it's just the computations sort of come out that way. I also, by the way, as I mentioned here, I get a first order correction term to the result, which explains in this data why the first number is a little bit bigger than 1/2, and the later ones tend to be a little bit smaller than the geometric probabilities. All right, but now, for Avanti, here's the last slide. What about dimension d greater than or equal to 2? Well, here's Svante's conjecture. So let's use the same notation. P tilde mk is the fraction out of the first m records generated that break k records. The claim is there's a limiting distribution in this case too, but not geometric. I'll call a random variable with that distribution b. And the question is, what is that distribution of b? The claim is it's a mixture. I'm using sort of standard mixture notation here. For those of you who are more statistically oriented than probabilistically oriented, let me put it in prior and posterior distribution type terms. That is, if we take x, the prior distribution to be exponential with parameter 1, and then take, look at the Poisson with that random parameter, right, like this, that's the distribution I'm talking about. So choose, I'll say it again, choose x, distributed exponential 1, condition on that, now take a Poisson with this parameter, and then the claim is that that's the distribution of b, right? Now, so you wonder, wait a minute, does that even work out correctly when d equals 2? Because I'm talking about an exponential mixture of Poissons with parameter x. Is that actually geometric with success probability half? And the answer is yes, you can work that out analytically, or you can realize that what we're talking about is the number of arrivals in a unit intensity Poisson process before the first arrival in an independent unit intensity Poisson process. And by easy memorylessness arguments, you see that that's going to be geometric with success probability half. So we had a different conjecture before Svante came along, at least about the probability that b equals 0. We thought it was 1 minus 1 over d. But a word about our simulations, it becomes harder and harder to generate these records as d becomes larger and larger because the rejection probability goes way up, right? And so even generating, 1,000 observations in 1,000 records in dimension 6 or 7 becomes really slow. So we had a relative paucity of data, and we thought, well, okay, it looks like maybe the answer is 1 minus 1 over d. That's not what Svante says, but it's not so far off from what Svante says either. So we actually looked at the entire distribution of b for dimensions 2, 3, 4, 5, 6, I think. And it's hard to say, without, we didn't carry out formal statistical testing, but yeah, but it looks as if maybe this is the right answer. And Svante has some fairly convincing heuristic arguments why this ought to be true. That's another great project for Ao Soon is going to work on this stuff, or somebody else.
Or for a statistician, get the code.
Yeah, right.
Generate, get a p-value that says reject Svante's conjecture. Right. And then hope your code's right.
And also find a way to generate in high dimensions. We don't, it really slows down badly at around dimension 6 or 7, right? We can't go up there. All right, so that's all I have to say.
Oh, sorry.
Yeah, you can.
Oh, well, let us I was just wondering, for d bigger than 2, is there some sort of description of this distribution that, like, you have this d equals 2
what?
Description, number of arrivals, interpretation of that.
Well,
that
sure,
distribution.
right?
D bigger than 2?
Sort of, right? You could say, so the reason why the explanation works in the case d equals 2 is partially because x is distributed exponential 1. So you're waiting, so independently of one process, you're waiting for the first arrival in something else, right? But in the case d equals 2, this reduced just to x. So you're saying Poisson up through a particular time, and that time is this independent, waiting time till the first arrival in a different Poisson process. Putting on the power d minus 1 and dividing by d minus 1 factorial,
But the way
that's what I'm asking. That's what I'm asking.
Yeah, maybe there's a story, right? Like, what would it mean to sort of, again, in d equals 2, it's like x is the time in the Poisson process. So if x is the time in one Poisson process, what does it mean to do x to the d minus 1 in the other one? I'm not sure.
Okay.
Yeah, I don't know if there's a.
But is there a reason why you choose this mixture formulation rather than, I don't say that, that B, probably the B equals K, is some gamma function, something like that?
Well, so Smanta's not here, but I'll try to answer for him. So I think, as I recall, I didn't have time to review this in detail before the talk, but as I recall, the heuristic is that we know something of, I'm going back to the frontier picture. We know something about, fairly precise about the number of points along this boundary, along this frontier. And the question is, how are they spaced? And by the way, that's another completely open and very interesting question to ask. You know, at a microscopic level, what does this boundary look like? Saying it's approximately linear, okay, that's a 0th order approximation. But what's or first order? What's the next order approximation? But so his heuristic says that they're spaced like a Poisson process along here. And then from that, it's not too hard to get to his conjecture. And the x to the d minus 1 divided by d minus 1 factorial has to do with computing the volume of a certain region that would correspond to breaking a certain number of records if you knew the number of current records within that region, right? And again, his heuristic says they're about a Poisson number. Now, whether that's right or not, I don't know. I mean, he didn't I talked with him too, in addition to his writing some stuff down. He said, I don't see any reason why it wouldn't be Poisson.
So we have to invite him.
Yeah.
That's not a bad idea.
Inviting Svante Janssen always pays off. Like, get your 10 most interesting open problems and give them to Svante for an afternoon, and he'll solve 5 of them, and 5 the next day. So, yeah.